Now, Valerio Di Maggio will speak about an unconventional introduction to deep learning.
Thank you. Thank you very much for being so many here. So the idea I had with this talk is to give you a sort of unconventional introduction to deep learning. Deep learning is quite a buzzword today. Many people talk about this, and it's quite popular topic, and many talks around. And I believe we're going to have different introduction to deep learning to the PyData track in Python. I try to make it a bit different, and this is the unconventional way I had in mind. So it's trying to talk about this topic in different perspective. The metaphor I'm going to use in the next slides is just like this one. In case, probably if you come from Great Britain or UK, you already know what it is. Otherwise, I will tell you later. But this is the hint. It's related to Doctor Who sometimes. So the quite uncommon deep learning introduction is that deep learning has proved to be very effective in many fields, many topics, especially image segmentation, image classifications, and sometimes it's always said that perhaps it's better than human in doing some specific task. The other quite common introduction about deep networks and deep learning is that is more or less related to the neural networks we actually have in our brain. And this is where the name comes from, indeed. So this is a quite standard neural network, especially a deep neural network. So you have input, result, and lots of layers and neurons stacked all together. To be more specific, this is a multi-layer feed-forward network that starts with an input layer here and proceeds with fully connections, which you have followed by a list of hidden layers, so-called the hidden layer, and separated by non-linear transformation. Okay, so this is the general description of this picture. But I believe, if I'm not from the field, that doesn't really make any sense. Okay, so I try to see more into the black box of this very deep neural network. But it's quite simple if you take a look at it from different perspectives. The same network I showed before is just like this input layer, and the hidden layers are connected in this way. So what you have is that a series of connections from each point here to each other point in the next layers, going from left to right. So you pass the input here, and you get the output in this in the very last stage. At each step, what you do is just like having the calculations here, which is a very linear operations. It's a combination of these two layers, and each element here is just a neuron. And after you have just computed this product, you have some non-linear activation. So you have the set of weights here. This is the weight connections. This is the bias. And this is the non-linear function at the end. This function could be any kind of non-linear function. Typically, is ReLU or sigmoid or tanh. This is quite common names if you're a bit into the field. But and this is the result of this computation is the layer activation you get. And this operation is basically repeated for each layer. And so you do this computation, which was exactly what I displayed in the previous slide. So the previous slide was just the calculation of this function and this input here. And the same is repeated for each layer. Okay? So y0 here is for the first layer, y1 is for the second layer, and so on and so forth, till you reach the last layer. Okay. In particular, if you apply this kind of network to an image classification task, what you have in the last layer is the set of classes you want to classify. So if an image classification problem, what you expect is passing images as the input here. You map each pixel of the image to one neuron in the very first layer, so the input vector, And then you expect that the network provides you a class, or better, a probability of the most probable class for the image you passed. This is quite standard. This is a task where deep networks prove to be very effective. Summarizing a bit, the neural network is built from layers, each of which is a matrix multiplication, then add bias, then apply nonlinearity, and these appends for each layer. And what the learning has to do is just to learn the parameters of each layer. And this means learning the values for W, so the Sato weights, and B, which is the bias. And for each layer, the technique used to learn this process, so the values of these parameters, is called the backpropagation. So very naively and very quickly, the idea is that you start with a set of random weights, you pass the input till the output, you get the output, get the values. So if you get an error, you basically want to correct this error. And so you start correcting the error from the last layer back to the previous one. And so that's why you call it backpropagation, because you backpropagate the error corrections till the very first layer. And you do it by calculating the gradient, okay, because you want to optimize. Typically you want to minimize the error, so you want to follow the negative directions of the gradient. And so lots of mathematics and functions comes into play. So you have the loss function you want to optimize, the activations, and plus all the parameters of the model. Deep networks comes in different flavors, actually. You can talk, the very simple example I showed you was about a feed-forward network. So a network that gets data from the left and provides output in the very last layer, and there's only connections between each layer and the next one, okay? And every layer is fully connected to the next one. So these kind of networks are called feed-forward network. A very specific type of these networks are the convolutional neural nets. We will talk a bit about these ones later on. And the difference is that when you pass from one layer to the next one, you want to apply a convolutional operations, okay? And this is what, if you don't know what a convolution is, please wait a minute, I have some slides for it. Next flavor is recurrent neural network. The difference here is that you have connections between layers. So you have connections and also backward from one layer to the previous one, probably, perhaps. And the general idea of this kind of network is that they can learn from sequence data. And so you want to learn to generate the next part of a sequence. And this kind of networks are said to have memory. In fact, this model here is the long short-term memory network. It's quite effective for lots of tasks. And the last set of flavor for networks are very interesting models for unsupervised learning. Previous ones were for supervised learning. So in case you have labels for your data, you want to make classification or regression in the general case. But in case you don't have any and you want to do unsupervised learning, there's these kind of networks very interesting, and any variation of this one that tries to learn directly from the data. So this is the case of autoencoders. And so you have restricted Boltzmann machine, deep belief nets, generative adversarial networks, lots of terms that I believe doesn't really mean anything to you at the moment if you're not at the case. So that's why I said the deep learning is quite like the TARDIS. It's very bigger on the inside, because when you just talk about it, it's lots of details, okay? And you have to cope with it. There's a lot of things you have to know, and you always have to live with it and keep on being updated on it, because many papers are published every day. And so that's why I wanted to talk a bit more about this in a different perspective. So what about Python in this? the very first question I asked myself when I first came up with these kind of problems was that we had a very long list and series of machine and deep learning libraries are all the same. So that's the very first question I asked myself. And the answer is no. Mainly because these libraries, quite popular for machine learning, they totally miss the support for GPU computation. Okay? The key for deep learning, for an effective deep learning, and when I say effective, I mean in terms of performances, computational performances, is having GPUs. Okay? Because the computation of what you have to do with deep networks is definitely more efficient on a GPU rather than on a CPU. And this is because GPUs are better for matrix algebra, even if they're in the very early stage. GPUs were supposed to be designed for games, for graphical computations, okay? It's quite the case for deep learning, but with a slight difference, and I will tell you very shortly what's the difference. It's very good at parallel calculations, and so if you have a process and operations that you can parallelize, it's definitely better to have multi-cores, because you have many cores, many more cores in a GPU rather than what you have in a CPU. The very difference, so it's much powerful in some sense, but the very difference is that you have, the drawback of this, is that you have less memory on a GPU with respect to what you have on a PC, so CPU and RAM, of course. So let's try to understand why GPU can be effective. So this is a very quite popular network. This network is called the VGG16. Okay, this network is a convolutional net. It's a fully connected convolutional net. So this means that you have 16 layers. That's why the name. You have 16 layers. On each layer, all these layers are convolutional layers. So this means that you apply convolution operation. And in the end, you have fully connected layers, okay? And the very last one is softmax. This layer has been the winner for the ImageNet classification task. So this task was, you have millions of images, and you want to predict 1,000 of classes. So you provide to the network any image you want, and the network has to distinguish this image among 1,000 classes. The vanilla version of this is just, let's depict this as convolutional filters here and fully connected plus the softmax, which is the prediction layer in the end. So I came across this paper. It's quite interesting. So if you compare the operations and the time required to do the operations inside the network, regardless it's the GPU or the CPU, most of the time, both the two architectures spend a lot of time in doing the convolutional operations and the fully connected layers. Okay, so most of the time is spent in this part of the network, especially in the backward pass. That's the most, let's say, the most time-consuming operation. But please take a look at the difference in timing between GPU and CPU, and this paper is not very up to date. So this means that the architecture compared here are definitely older than what we have now. And this is the case of CPU and GPU as well. So in particular, in this case, we're talking about a batch size of 256. This batch size is now the keyword, and this means that you provide to the network, and the network learns from 256 images for each step. Okay, so the network gets 256 images every time. So there's this library, this function in the BLAST library, which is called GEMM. GEMM stands for Generalized Matrix-to-Matrix Multiplication, and this is actually the heart of deep learning. Okay, in case you cannot remember, this is what a matrix multiplication is. So you get two matrices here. So you want to multiply a row, this row with this column, and you get this value here. Okay? So actually, why I'm telling that GEMM is the art of deep learning. By the way, the very difference in case of general case for graphic computation on GPUs is in the scale. If you are going to in just one single layer of a typical network, for instance, you may require to multiply this matrix here of these dimensions, so 256, because we have 256 batches. This is the case of VGG16, for instance. Times 1152, okay, by these other matrices here to get this result, okay? This is just one layer, and you have to repeat these for each layer. And this just requires 70 million, just very naive calculation, requires 70 million flops just to do this operation for one single layer. And you have to repeat these kind of operations, more or less, of course, with different sizes, but in the general case, you have to repeat these kind of operations for each layer. And then that's for the forward pass, and then back for the backward pass, okay? So lots of computation running. That's why GPU may be so effective. So that's the very simple case. So the fully connected layer. The fully connected layer is just this one. You have the input X, you have the weights W, and then this is what you got. Okay, so it's definitely a matrix multiplication. It's the very simple case. So GEMM is actually used to implement this operation. Oh, by the way, the matrix multiplication is a highly parallelizable operation. You can highly leverage on parallel computation on this. In case of convolution, that's the very simple representation of what actually a convolution is, in case you don't know. This is the case of images, because convolutions are applied to images most of the time. So we're still talking about images. Images are just like matrix, but they have an additional dimension, which is the depth. So in case you are dealing with black and white images, you also have the third dimension, which is the channel. Most of the time is RGB channel, okay? So in RGB you have 3 channels, and so you have one matrix for each channel. And so you have then the convolutional network. And so what you want to do with it is just to provide, so it's just to multiply this little cube here for each part of the original image to get the output, and this output is called the activation map. For many reasons I don't have the time to tell you now, but if you want, please ask after the talk. So this is actually how the convolution works. So you basically have the convolutional filter here. So it's actually a matrix of numbers, and you want to pass this filter along the matrix. And when you do this operation, what you're doing actually is just a matrix multiplication. Okay, and that's why GEMM can be definitely useful also in this case, even for convolutional nets. The real implementation of convolutions in real code is this one. Actually, the convolution is implemented as a very large sparse matrix, because with these, so basically the convolution is the input multiplied by these matrix here, the convolution. And in each element here of the convolution of this matrix C, you have the weights of the convolutional filter repeated. This is a sparse and let's say big representation of the kernel, but of the convolutional kernel. But this is quite effective, especially because in case you want to do the opposite operation, so the deconvolution operation, which is quite the case for images especially, you have just to transpose this matrix, and it's very effective to do it. Okay. So this is why. So this is the computational perspective. Okay. So the matrix multiplication perspective, and so the very raw level of what actually a deep network is doing during the learning process. So what about Python and the deep learning frameworks? There are many frameworks nowadays. Torch, TensorFlow, Theano, Caffe, and many others, and each of which is implemented and or has APIs in many languages. There's Lua for Torch. Actually, nowadays there's also PyTorch, which is quite popular nowadays. So you have many levels here, reaching up to the hardware in the very last stage of this long pipeline. Typically, the NVIDIA GPUs are applied in deep learning, but there's no reason why you cannot apply others GPUs from other vendors, but NVIDIA is the most famous one. And so these libraries are organized in two different categories. You have model specification based, so you have configuration file in case of Caffe or CNTK. CNTK is the one from Microsoft, versus programmatic generation. And this is especially the case of Torch, Theano, and TensorFlow. And the last one is the one I'm going to talk about. So I'm going to explain very soon what programmatic generation is. Then, from a very programmatic perspective, they differ for the language they use, Lua versus Python typically. And Python is quite heavily used for Theano and TensorFlow in case we're sticking with this programmatic generation. Okay. So what's the difference between TensorFlow and Theano? Theano is a deep learning library with a Python wrapper and inspired a lot TensorFlow. So actually what TensorFlow is actually now, it's thanks to Theano, what Theano did many years ago. TensorFlow is a deep learning library from Google, has been released open source quite recently with respect to Theano, which is a university laboratory project, community-driven project. Theano is quite the same of TensorFlow. The very difference from TensorFlow is that Theano lacks any support for distributed computation. This is actually where TensorFlow is winning right now, because it's supposed to run on a cluster. Guys from Google says that they use actually in production TensorFlow. Of course, perhaps it's a different implementation of TensorFlow with respect to what we have, but it's running in a Google cluster infrastructure. So that's why it has this great support for distributed systems. What does TensorFlow provide? It provides primitives for defining functions on tensors. So you already get from the name, probably. Tensor is the most fundamental structure you have here. And the other important feature TensorFlow provides is, and this is also the case for Theano, is automatically computing their derivatives, and so the optimization is provided out of the box by these frameworks with respect to what you have to do on your own when you use, for instance, NumPy or whatever you want. Okay. So what actually is a tensor? Generally speaking, a tensor is a multilinear maps from vector space to real numbers. So a scalar is a tensor, a vector is a tensor, a matrix is a tensor, but indeed there's been sort of problem here. So actually, I've read this tweet a few days ago by Matthew Rockling saying that please stop calling multidimensional arrays a tensor, because actually it's not quite the case, especially if you're a mathematician or a physicist. But we may say, it's quite legit to say, that an intuitive way to see or to represent a tensor is as a multidimensional array. Okay, so let's keep with this metaphor in mind. And in terms of code, we can compare the dictionary from NumPy and TensorFlow. It's very similar, isn't it? We have reshape here. We have, this is for the element-wise operation. We have zeros as well. The sum is called the reduced sum in TensorFlow. And the dot operation, so the matrix multiplication, the very important one, is called the matmul in TensorFlow. But you can handle tensors or multidimensional arrays in TensorFlow or in NumPy very similarly. The very difference is in the computational model that runs in the backend between the two. So if you have these very simple and stupid lines of code, So you want to initialize an humpy array, 2 times 2, of zeros here, and then using the TensorFlow library, and you want to print here A, so it's the numpy array. This is what you got, and of course, it's quite expected. But in case you want to do the same with the tensor created with TensorFlow, this is actually what you got. It's a tensor object, okay, with these properties. So it's float 32, this shape, this name, automatically generated, but this is not the same. To get the actual result here, what we have to do is to evaluate these expression. And this is especially because of the computational model TensorFlow uses to perform operation. This computational model is called the TensorFlow graph. Okay, the idea, and this is the case why these operations work for machine learning, is that you can implement machine learning application as a result of repeated computation of complex mathematical expressions. And so you can describe this set of operations as a data flow graph. In this data flow graph, you have each node representing the instance of one single operation. For instance, multiplication, addition, division. Each edge in this graph is a multidimensional data set, in this case a tensor, providing the data on which the operations are performed. So more specifically, for TensorFlow, you have the instantiation of an operation as a node, okay, and each operation has, TensorFlow calls this as kernels. So you have an operation is one that has inputs greater than 2 and outputs greater than 0, of course. And you have data edges, so the set of edges carrying tensors, so providing the data between operations. And you also have dependency edges, so the edges you set in a graph to establish dependencies between one operation and the other one in terms of order of execution. This is particularly useful in case you have multiple layers stacked one after the other, and you have to compute the previous layer before going to the next one. This represents a computational graph in TensorFlow before and after graph transformation for partial execution. And this is particularly interesting because TensorFlow allows you to have also a partial execution of the graph. And this is why I told you before that TensorFlow has support for distributed computation. This means that this graph can be executed completely from 2 different nodes. Or in case you don't want to distribute the computation between different machines, you may also distribute the computation between the multiple hardware you have on the single machine. For instance, imagine you have 2 GPUs, 4 GPUs, okay? You may tell to TensorFlow that you want to execute this part of the graph on one GPU you have, the other one on the other GPU, and the last operation here may be on a CPU, because it doesn't really care if you want to, you get any gain, real gain, if you're executing that node on a CPU or GPU. It may be the case. So this is the example of a very simple one of a graph generated for a very simple model here, which is the logistic regression here, very simple logistic regression function model. Okay, so this is how TensorFlow represents, in terms of nodes and operations, the computation of these classification function. In case you have multiple layers, okay, this is a very interesting animations I found on the web. You find the reference here. It's very interesting because you see how TensorFlow works when you have multiple layers. And you start with these embedding. This is a sort of vectorized representation of words. This is called embedding in this particular case. And you can see how TensorFlow basically replicate the operations among the different layers. So in the last minutes, thank you. In the last minutes, I would like to show you how you actually implement and what actually means using TensorFlow to build a neural network. For sake of brevity, of course, we will just implement one single logistic neuron, which is just one single layer of network. So it's very simple and stupid. This is the loss function and the update rule for the optimization. And so we start creating the, this is TensorFlow syntax, okay? So we are not, we are just initializing the model here. So we have X and Y. And we specify two placeholders. So in terms of TensorFlow, you're basically specifying that these two variables should have, should be of float type and have these size, shape in terms of tensor. Then you set the model weights, so W and B, it's the very simple one. Okay, we create variables here. And again, here we're not providing any data, we're just setting the symbolic way to, in a very symbolic way, what the memory allocation should do in the next steps when we are going to evaluate these operations. We then construct the model here, and we have this softmax in the end. And the input to the softmax is the matrix multiplication between x, w plus b, so the very logistic neuron, okay? So the linear operation plus the bias. And this is going to be the input for the softmax, which is the activation layer. And this is for the optimization, okay? So we define the loss function here, which is the cross entropy. We want to minimize these cross entropy loss function, and to do it we want to use, of course we have to repeat these operation. In case we have multiple layers, we have to repeat exactly more or less the same operations here for each layer we want to add. And so the input for the next layer would be the output of the previous one. And afterwards we specify the optimizer here. The technique, or the optimization technique we're using here is the gradient descent optimizer. So it's quite popular technique for the stochastic gradient descent actually. And finally, we initialize all the variables. So when we call this here, okay, this is where the actual magic happens, because after we are set all the network configuration and all the layers and all what they are supposed to store in memory at each step during the execution, we have to implement this for loop here, which is actually the instantiation of objects in memory. And so these loops goes from, for each epoch, which is the number of times you want to iterate the network learning, okay? In this case, I'm using images, so the MNIST dataset is quite popular. So in case you don't know what it is, please ask. So we're organizing data in multiple batches, okay? So a subset of images for each step of the network. And then we are basically calling this session run instruction, where we basically provide what's the actual content of X and Y. And X and Y get the values corresponding to each batch. And the feed dict is the parameter we have to set to actually pass the objects and so fill the data into memory. And this is automatically provided by TensorFlow. So very quickly, what does this loop do? Does this loop do? Is basically iterating for each epoch, for each batch. It's calculating the optimization here for the batch, calculate the cost function, sum it up for average cost, and then pass it to the next batch, where X and Y will get two new values, and repeats this for each batch and for each epoch until the network supposedly has converged to learning. Okay. So this is a very simple implementation in TensorFlow. What's next? Actually, we have a tutorial on deep learning the Keras way. I'm doing it on Saturday afternoon, I believe. And this is another library I would like to present you. This is Keras working together with TensorFlow. Keras is a quite popular right now, a library, and I will show you in this tutorial how you may basically simplify a bit from a very Pythonic perspective what you had written in pure TensorFlow code with, of course, pros and cons. And so that's it. Thank you very much.
If there is any question, we have just 5 minutes for some question.
Have you seen about the Intel Xeon 5 processors?
Yeah, never tried it, but as far as I understood, Intel is trying to avoid using GPUs to do it.
Yeah, they are with the same business of NVIDIA, of course.
Exactly, exactly, yes. But never tried yet. Never had a chance to try it yet. But I read a bit about the Xeon processors, and they claim to have better performance than GPUs, even if I think yesterday NVIDIA announces the new Tesla GPU. Yeah. So
yes. And another thing regarding the GPUs, it's not easy to change GPUs from vendors because NVIDIA has CUDA, which is a very good standard.
Very good point. Yes.
AMD has HSA, which is still ongoing, whatever it is.
Yeah, as far as I know, AMD has OpenCL support. Indeed, TensorFlow does not support different vendors than NVIDIA. It runs only on... by the way, a very important point here. TensorFlow runs with GPU and CPU as well. And this is always the case for deep learning frameworks. You can do what you do on a GPU exactly the same way you do on a CPU. Of course, it takes more time on CPU, but TensorFlow implements kernels operations both for CPU backend and GPU backend. But anyway, TensorFlow supports only NVIDIA GPUs. Theano, instead, is now supporting as a very primitive support for AMD cards. So in case you have it, I have a colleague of mine who's trying to use Theano on the very latest MacBook Pro. They ship with the AMD card on it. So he tried to make it working there.
Thanks.
Yeah, thank you.
Last question.
Okay, I have two last questions.
Oh, please.
Okay, the first one is there a method or something that allows you to decide in an optimized way the number of hidden layers and hidden neurons for each layer? Or is something more like a trial and error?
Yeah, most of the time, on my own experience, most of the time, doing it by heart definitely works better.
Okay.
But that's a very good question, because this is a very open issue for these kind of models, because you have lots of hyperparameters here. So apart from the parameters you have, and when I say parameters, I mean all the parameters inside the network, so the billions of flops operations I was talking about previously, you have lots of parameters for the network, so the number of layers, the value for the learning decay, for the momentum, for the regularization, put it or not, in case you have dropout. So I'm talking about buzzword, I know, but it's a lot of hyperparameters. There's no answer to it so far. You have models, you have techniques to optimize it, but most of the time it's very time consuming, and the improvement you get is not very effective with respect to the time required to do the operation.
I see. The second question is more like a curiosity of mine. From what you said, it seems that deep learning is about, it's only about fully convolutional neural networks.
Okay, not really, no.
And that's true?
No, it's not.
Oh, it's not.
No,
okay.
no. Fully convolutional is because it's the example I decide to show you because it's the most intuitive one, I would say.
Okay.
But there are plenty of networks. You have recurrent networks, as I said. You have autoencoder networks, and this is also the case for adversarial networks, generative adversarial networks. You have many networks and different models here. So it's not just fully forward.
Okay, thanks.
You're welcome.
So thank you, everybody, and big thanks to Valerio.
Thank you.